I mentioned in the previous chapter when we were reviewing things like Lewis structures that representing molecules is very important in organic chemistry because even though in Gen Chem you relied very heavily on molecular formulas to describe a particular compound, in organic chemistry that doesn't quite cut it because there are so many different isomers, that is, molecules that have the same formula but are different. Okay, so we need to look at how to represent molecules to avoid a lot of the confusion that would arise from having, just relying on our molecular formulas alone. Okay, we also have to look at ways to conveniently express these molecules that can, so that we don't have to spend ages drawing every single bond in a Lewis structure. So in this chapter, we're going to look at how do we do that? How do we represent the molecules that we want to describe in organic chemistry? Okay, now there are different ways to represent molecules. So we're going to have to trade off between having a lot of detail with having, a lot of detail but also a lot of work versus having less detail but, taking less effort to express our formula. And you can see this is kind of a spectrum, right? So if we start all the way on the left, we have Lewis structures where we draw individual atoms with individual bonds. Okay. On the right, we have molecular formulas where we're just representing how many, atoms of each element make up our formula, and we just write them in order. Okay. Now, there are sort of stepping points or ways to break this down so that you can kind of trade off a little bit here. So, for example, we can take sections of our Lewis structure and condense them down into what's called a partially condensed structure. So, for example, instead of drawing these individual carbon-hydrogen bonds, since they are attached to this carbon over here, we could write that as CH3, or since we're going from left to right, H3C. Okay, and likewise, we don't draw that oxygen hydrogen bond explicitly. We can just say that hydrogen's attached to that oxygen just by writing OH. All right. Now you could take this a step further and do this for every atom. So in the case of this central atom here, we can write out, just write that there's two methyl groups, two CH3 groups attached to it. Okay, and a hydrogen that's attached to it. Now, notice that if you're not familiar with these fully condensed structures, it's kind of hard to read this, right? You've got to kind of get in the habit of recognizing that when someone writes something like this, you get a mental image of one of these things. Okay, you have to look at this and realize, oh, here's a carbon. I know that carbon has 4 bonds to it. What's connected to that carbon? Well, there's going to be two CH3 groups. Okay, and those two groups are connected, are two of my 4 bonds to my carbon. There's a hydrogen. Oops. There's a hydrogen connected to that carbon, and there's that oxygen from my OH group that's also connected to that carbon. Okay, so again, that takes a little getting used to if you haven't seen one of these before. Okay, now with let's say we have three structural formulas of three isomers of propanol, right? So here we have what's known as 2-propanol or isopropanol, to use the common name, rubbing alcohol, if you're familiar with that one. Here we have regular 1-propanol, and here we have an ether, ethyl methyl ether, right, or methoxyethane. Okay. Now all three of these have the same molecular formula, right? C3H8O. But we want to be able to draw this out to distinguish between these three molecules, which are clearly different. Okay, so again, just writing out the molecular formula wouldn't be enough to do this. So how do we draw this out? Which of these methods can we use to help describe these? Well, in the case of our Lewis structure, you can see all three of these are drawn out as Lewis structures, and clearly that works, right? But obviously it's a lot of work because you've got to draw those individual bonds, right? That takes some time. Would the partially condensed structure work for this? Yeah, it probably would. All right, we could see that if we condense this down, we'd still see that that alcohol group is attached to that middle carbon versus for propanol, we could see that it's attached to that carbon on the end, right? And even with our ether over here, we'd see that the oxygen's kind of in the middle and not attached, branching off to the side. So a partially condensed structure would work here as well. Even the condensed structure, I think, would work pretty well. But again, it might be a little bit, if you're not as familiar with condensed structures, it'd be easy to make a mistake when looking at your isomers of your two alcohols here. Okay, so my point is that that gets the job done, but it's definitely not infallible. Now, we run into problems when we get into larger molecules. So the example I previously showed you had only 3 carbons, right? What happens when you start dealing with larger biomolecules? So for example, here's an antibiotic, amoxicillin, and here's the Lewis structure. This includes a lot of detail. We see all the bonds, but the problem with all this detail is now that this structure is very cluttered. Okay, it's really easy to get kind of lost in this when you're trying to look for a particular part of this molecule. Okay, so sometimes drawing things less detailed is not a bad thing. Like even though it's almost like if you see too much detail, you kind of get blinded to what you're looking for. It's kind of missing the forest for the trees in a sense. So we want to take a diagram like this and draw it in a less cluttered way that makes it easier to see things. Okay. Plus, it doesn't hurt that it would be probably quicker and easier to draw. Okay. So that's where bond line diagrams or organic shorthand comes in. Okay. So this is typically how an organic chemist would draw a molecule. Okay, so notice that this structure is definitely way simpler and way easier to look at and kind of get a glimpse of what functional groups, what structures are we actually looking at. Okay, so now this is probably going to be your first introduction to drawing these types of molecules. And just like with condensed structural formulas, it takes a little getting used to. You kind of have to get used to looking at a bond line diagram and recognize what does this translate into in a Lewis structure. But just like with any language, once you start, you train yourself to recognize these things, you start thinking in terms of these structures, and recognizing these becomes just natural. Okay, so part of becoming an organic chemist or learning to do organic chemistry is getting comfortable with this way of representing molecules. All right, so let's look at the first steps here. How do we make our Lewis structures easier to draw with these bond line diagrams? Well, the first way to do this is we take out carbons. Okay, it's understood that organic compounds have carbons in them. We avoid drawing in the letter C for carbon because it's understood that the main backbone of our organic molecules are carbon-carbon bonds. So to show this, we would describe a string of carbons bonded to each other using a zigzag over here. Now, why do we use a zigzag? Because remember, carbons with 4 bonds are tetrahedral in shape. So that bond angle between a carbon-carbon bond and another is going to be 109 degrees roughly. Okay, so in order to represent that there are multiple carbons here and they are connected to each other, we draw this line in a zigzag so that each bend in the line represents a carbon. So if you drew this as a straight line, it would be tough to see where each of the individual carbons are. Here, by drawing our string of carbons in this fashion, it's easier to tell how many carbons are present. Now, don't forget to count the ends of the line as carbons as well. So in this example, we have 1, 2, 3, 4, 5, 6 carbons present. Okay. The other thing besides the letter C for carbon that we have missing is we also omit hydrogens. You probably noticed that if carbon likes to form 4 bonds, well, even if we've drawn all the carbon-carbon bonds, we're missing other things, right? You can assume in these bond line diagrams that all of your carbons have the 4 bonds necessary to help them meet the octet rule. So whenever you look at a carbon in a bond line structure like this, you can assume that it has enough hydrogens to help it meet that octet rule. And so accordingly, you can count that out. So for example, if you have a carbon on the end over here, okay, and it's got one carbon-carbon bond shown by this line over here, how many hydrogens must it have? Well, this carbon must have 3 hydrogens to help it make 4 bonds. Likewise, look at one of these carbons over here. This carbon has 2 carbon-carbon bonds, so it must have 2 carbon-hydrogen bonds to give it 4 bonds. So there's 2 hydrogens that are omitted over here. All right. So again, the nice thing here is we can we can draw out things relatively quickly and easily. Here we have 3 isomers of the molecule C6H14, and we can see that drawing them out really quickly like this saves us the hassle of trying to draw Lewis structures and play around with them accordingly. Okay, so over here we have hexane. All right, so it's got 1, 2, 3, 4, 5, 6 carbons. All right, and the 14 hydrogens are spread out where you've got 3 hydrogens on these terminal carbons, and these internal carbons have 2 hydrogens each. Okay, and again, that helps them meet. Each of them has 4 bonds that way. Okay. Likewise, look at this molecule here. This is 2-methylpentane. Don't stress about naming these so far. We'll talk about how it gets that name in a later chapter on alkanes. But for now, realize that if we look at each of these carbons, ask yourself, how many hydrogens does each of those carbons have? Okay, so you can see where the carbons are, right? There's 1, 2, 3, 4, 5, and the 6th carbon's up here. Okay, and based on the number of bonds that these carbons have, you can figure out how many hydrogens they need to get to 4 bonds. So each of these carbons at the ends of a line have 3 hydrogens on them. This carbon with 2 bonds, 2 carbon-carbon bonds, has 2 hydrogens, as does this one. This carbon has only 1 hydrogen on it, because it has 3 carbon-carbon bonds coming off of it, so its 4th bond must be to a hydrogen that's not shown. Okay, and here's 2,3-dimethylbutane, and I think you guys can kind of do that yourself. Here's 1, 2, 3, 4 carbons. There's the 5th carbon and the 6th carbon over here. And again, you can figure out where the 14 hydrogens are on this. Well, just to make sure you get it right, there's 1 hydrogen on this carbon, there's 1 hydrogen on this carbon, and each of the other carbons are terminal, and so they have 3 hydrogens each. Okay, so far we've looked at examples where we draw, where we've only had single bonds. What do we do with carbons that have double or triple bonds? Well, we still have to represent them in our diagrams. Now, double bonds are pretty straightforward. You just draw a second line here. The bond angle, the way we draw it, again, we're just drawing a rough representation. So even though that bond angle should be 120 degrees, because that sp2 carbon is trigonal planar, again, you're still drawing it as a zigzag. So, whether it's 109 degrees or 120 degrees, it's kind of hard to tell just by glancing at it. But again, that's not really important, right? You can tell it's an sp2 carbon from the fact that it has a double bond coming off of it. Okay. Now, with sp hybridized carbons, as you'd expect with a carbon-carbon triple bond, we have a linear system here. So you've got to be careful about, 1, how you draw this, and 2, how you count out the carbons. Because remember, since these carbons are in a straight line, you have to distinguish where carbons are. You don't have that zigzag to help point out every bend in the line as a carbon. So to do that, we have to be careful when we draw our triple bond and draw it between those 2 carbons that have that triple bond. So in this line here, I actually have 4 carbons. There's 1, 2, 3, and 4 carbons. All right. Now, please notice the lack of a zigzag, because remember, your sp hybridized carbons are linear. You cannot draw them with a bend in them. Okay, they have to be drawn in a straight line like this. But again, you use the triple bond to help show that there's a carbon here and here. Okay. All right. So as I pointed out, we don't draw the hydrogen, so you have to get comfortable with recognizing hydrogens that aren't there. Okay, you have to look at your bond line diagram and just intuitively figure out, okay, I see this many bonds. How many more bonds do I need to get to 4 bonds? Okay, and that is basically your way of counting hydrogens. Okay, so we practiced that earlier on a previous slide, but again, general rule of thumb: if you have only one bond coming, off of your carbon, it must have 3 hydrogens to make up for that. Okay, if there are 2 bonds coming off your carbon, there must be 2 hydrogens to make up for that. And of course, if you have 3 bonds to your carbon, there's 1 hydrogen, and if your carbon has 4 bonds, it can't have any hydrogens, right? Because it's met its 4 bonds to give it, 8 electrons to meet the octet rule. All right, so take a second and practice with a problem like this. So look at this molecule and ask yourself, how many carbons and hydrogens are here? Okay, so be sure to, again, remember every bend in a line or every end of a line that isn't otherwise labeled with an element is a carbon. And don't forget each carbon must have 4 bonds to meet the octet rule, so count accordingly. Okay, so feel free to pause this video and try this problem out yourselves. Okay, and then I will move on to the actual answer. So you should have 15 carbons and 19 hydrogens. So if you're having trouble seeing that, I'm going to count out the carbons accordingly. So please note here that we have a sulfur and a chlorine present. Okay, so those are not, obviously those aren't carbons, right, or hydrogens. Everywhere where we've got lines that aren't marked with elements, those are going to be carbons. So we have 1 carbon here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, there's our 15 carbons. As for our 19 hydrogens, there are 2 hydrogens on this carbon. Okay, this carbon doesn't have any hydrogens. Notice that it has 4 bonds, as this double bond here, a 3rd bond, and a 4th bond going there. Likewise, this carbon doesn't have any hydrogens. This carbon has 1 hydrogen. Okay, it's got a triple bond to the carbon next to it, so it must need 1 hydrogen to give it 4 bonds. Okay, this carbon also doesn't have any hydrogens. This carbon here has 3 hydrogens, as does this carbon. This carbon doesn't have any bonds. This carbon has 2 hydrogens. This carbon has 3 hydrogens. This carbon has 3 hydrogens. This carbon doesn't have any hydrogens. This one has 1 hydrogen. Okay, because there's 1, 2, 3 bonds here to other carbons, so there must be a 4th bond to a hydrogen. So if I count that, that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I think the one that we always forget is there is a hydrogen on that sulfur. So that's the 19th hydrogen there. Okay. So, generally speaking, you want to, basically, if you're trying to take a molecule and draw it out, again, when you're drawing your carbon chain, start off by, drawing out the carbons using that sort of zigzag pattern. So here we have 4 carbons. So you start drawing out with, with a point, and then that's 1 carbon, then 2, 3, 4, and we'd stop there. Okay. Generally speaking, whether it's carbons or any heteroatoms that come off of it, like oxygen or sulfur or whatever, generally follow VSEPR theory. So, for example, here we're going to have a trigonal planar shape, right? This carbon has 3 atoms coming off of it. You want to draw that bond angle at 120 degrees or so. You don't want to draw an acute angle like this. Okay. All right. Now, something to watch out for here is that you can rotate around single bonds. So just because a structure is drawn in a particular way, you have to be ready to recognize those rotations. All right. So for example, if I rotate around this bond over here, so if I rotate this, basically 180 degrees, this carbon-carbon bond swings downwards over here. Okay, so if I were to rotate this bond here, I'd rotate it 180 degrees, this starts pointing downwards. Okay, and likewise, with the other side as well. If you're having trouble visualizing this, this is where having a molecular model kit kind of comes in handy, where you can kind of play around with this. And I highly recommend that, because if you start playing around with models and start, your brain starts developing that sort of spatial awareness, then you can start doing a lot of those manipulations in your head. But I think doing this physically with a model in front of you really helps build that skill. So if you don't have a molecular model kit, I highly recommend one. If not just this chapter, especially later on when we start looking at chiral molecules, we start looking at chirality, using a model kit really helps your brain to think in 3D. So that's a very, don't feel bad if it takes you a while to get the hang of that skill. It's not a very natural skill, but you will get the hang of it and you'll get better at it. But I find that using a model makes that a little bit easier. Okay, so if you want to play around with bond rotations and think about how many ways you could draw this molecule. So on the next slide, here are just a bunch of different ways we could rotate. We can rotate those bonds to get different shapes. So for example, if I rotate this bond 180 degrees, this flips down here. So that's why we get this molecule looking like that. All right. Likewise, if I rotate this bond 180 degrees, this whole piece swings upwards over here. Okay. And so on. You can play around with this in multiple ways, and this doesn't even include the entirety of it. There are multiple ways you could do this that aren't even shown here. My point is, just be aware of this being a thing. Okay. I think I pointed out that we have heteroatoms. That's atoms that are not carbon or hydrogen. You should draw them explicitly. So, for example, on that. In one of our earlier examples, we showed a sulfur and a chlorine in our molecule, and we wrote the symbols for those. Likewise, here we have an oxygen in our molecule, so we do have to write the symbol for oxygen. Now, if you have any hydrogens attached to your heteroatom, this is a situation where you explicitly should write the hydrogen. Okay, so even though we leave out hydrogens when they're attached to a carbon, we do write them explicitly when they are attached to a heteroatom like oxygen. Okay. Oh, and I think I've pointed this out, but again, you want to make sure you're still following all the rules you would with any Lewis structure, and one of those very important rules is following the octet rule. So never draw a carbon with more than 4 bonds. Okay. Carbon is incapable of violating the octet rule. Anything in the first and second period, or second period really, can't violate the octet rule. So you can't have more than 8 electrons around them. So carbon, being in the second period, can't have more than 4 bonds, because that would mean it has more than 8 valence electrons. Okay, so something to keep in mind. All right, so here is an example, a couple more examples of Lewis structures. Take a second and try drawing these out as bond line diagrams, as organic shorthand structures. Okay, so I recommend looking for that carbon skeleton, okay, that carbon backbone making the molecule, and then try drawing that first, and then think about what other pieces are attached to it. Okay, so pause the video here, take a stab at this, and then I'll talk about the answers in a second. Answer to that first slide, for that first Lewis structure that was drawn. So you can see that we started off with these, this carbon backbone here. So if we count this out, we've got 1, 2, 3, 4, 5, 6, 7 carbons, right? You want to be careful when you just start drawing a zigzag of 7 carbons, because it's this triple bond here that throws us off a little bit. So let's start off with just that side. So if we're connecting those 3 carbons, okay, we draw our zigzag like that. So it'll be like kind of like a V. Okay, draw these 2 carbons here with our triple bond, and then you can continue from there. So we'd continue from this carbon. We have 1, 2, 3 more carbons. So 1, 2, 3. there's a double bond between these two carbons here, so that's where you add that double bond in here. And of course, we have this chlorine coming off this carbon. Again, since we want to show that, we want to continue that sort of zigzagging pattern for this carbon-chlorine bond, you don't want to continue on this way, because then you wouldn't be able to see that there is a carbon here. It would look like that chlorine is connected with a very long line to this carbon here. So that's why we bend this line over here. We continue the zigzag in this direction. Other than this chlorine, everything else is hydrogen, so really you don't need to mark anything. That's why you kind of just stop here. Okay. With this molecule, you've got this carbon with two CH3s coming off of it, so that's where that's drawn. If we continue this backbone here, we've got 1, 2, 3, 4, 5 carbons. Okay, so 1, 2, 3, 4, 5 carbons. Okay. Now this fifth carbon here is part of this ring over here. So we have 4 carbons connected in a ring. So that's kind of why this square is drawn over here. Okay. We have, I think I pointed out these two CH3 groups that have carbons sticking out here. And there's one more branch over here. So that's where this one's drawn out. Okay. Now in terms of heteroatoms, this carbon over here has an OH coming off of it. Okay, so we draw that OH group. And again, how you draw it is fine. So here it's pointing downwards in this Lewis structure. If you had this angled this way as well, that's probably fine as well. So there's more than one way to draw it. Remember, you can rotate freely around this carbon-carbon bond. So there might be more than one conformation of this. Okay, so if you drew this slightly differently, that's fine. Like, just be ready to recognize that it could be drawn in more than one way. Okay, let's try a couple other problems. So here we have the molecular formula C5H9ClO. Now let's try drawing this molecule in different ways. So there are multiple molecules you could get from this molecular formula, so something to keep in mind here. I guess a good starting point here would be to start off by drawing your 5-carbon backbone and thinking about how you can connect your 9 hydrogens and your chlorine and oxygen. Okay, so do you have, for example, a double bond to the oxygen? Do you have a do you have a single bond to the oxygen, and then the oxygen bonds to one of your hydrogens to make an alcohol group? There's a few possibilities here. In fact, I think the answer slide it includes only 3, but there's obviously going to be a whole bunch more that aren't shown. I will give you the hint that this molecule does have it has what's called a degree of unsaturation. So there's going to be a double bond in this molecule or a ring. So one of those two things. You can either have your 5 carbons connected together to make like a pentagon, or I mean, you could even have a smaller ring and just have things branching off. But anyway, my point is that there's going to be either a ring structure or a double bond somewhere in this molecule. Okay, we'll talk about degrees of unsaturation pretty early on in Chem 204. So that's something to look forward to next semester. How I figured out just by looking at this molecular formula that there's a double bond or a ring. Anyway, so go ahead and try that out. The other problem to try out here is this structure. Okay, so here we have CH2, CH, then 4 CH2s. Okay, this is a condensed structural formula. All this bit over here tells us is that this carbon and this carbon are connected by 4 other carbons in a straight line, or well, a zigzag line, but in a continuous line. So in other words, I've got a 6-carbon chain here. This CH2 over here tells me that this carbon must be double bonded to this carbon. Okay, because this carbon has 2 hydrogens attached to it, so it needs 2 more bonds. It must be getting those 2 bonds by double bonding to this carbon over here. So really what we've got here is a 7-carbon chain, and there's 2 bonds, there's a double bond between these 2 carbons. So if I were to draw this out, it kind of looks like this. So 1, 2, 3, 4, 5, 6, 7. And there's a double bond between these first 2 carbons. Okay, so that's my CH2 four times is basically 1, 2, 3, 4. It's these 4 carbons drawn over here. That's the CH2 4. Okay, this carbon over here is that CH3. This carbon that's CH is this carbon over here. It only has one hydrogen sticking off of it. Okay, so for this one, you're going to rotate around these carbon-carbon bonds and see how many different conformations can you draw for this molecule. Okay, so go ahead and pause this video and try this out, and I will talk about that on the next slide. So here are some examples of the molecule drawn out the way it is. So these are 3 possible isomers from this molecular formula. As I pointed out, you can have a double bond somewhere. In this case here, it's between 2 carbons. Or you can have a ring structure. So here we've got a 5-membered ring. Again, this is just only 3 possibilities. There's lots more. You could have had a double bond with the oxygen instead of between 2 carbons. You could have had a 4-membered ring and had another carbon sticking out somewhere as a methyl group. But again, lots and lots of possibilities here. You've got a lot of atoms to play around with. Okay, so if you drew something besides these 3, that's totally okay. Okay, just the key thing is make sure that you've got the right number of atoms, especially hydrogens. Okay, if you didn't put in that double bond or didn't have a ring, you would have wound up with 11 hydrogens instead of 9. So that's how you can tell that, if you count your hydrogens, that's a quick way to check your work. Okay, and then as I pointed out earlier, here's your that long alkene, so that 7-carbon chain with a double bond at one end. And again, you can just rotate around these to get various conformations. And of course, there's multiple ways we can do this. So you could probably more than just these 2 ways. But the bond line diagrams are great because they unclutter your molecule. They make it a lot easier to see the big picture, like what's in this structure, rather than get bogged down with the level of detail in a Lewis structure. So, for example, here, when you're looking at a change in a molecule over a chemical reaction, typically what you're looking at is the change in a functional group. Now, functional groups are parts of organic molecules that, as the name suggests, have some sort of function. It turns out that your regular hydrocarbons aren't themselves very reactive, so usually you're looking for something, a part of the molecule that is reactive. So look at this example here. So here we have an alkene, right, which has a double carbon-carbon double bond, and we're doing a hydrogenation reaction where it gets converted to an alkane, where you only have carbon-hydrogen single bonds. Now, how do we tell that this reaction has occurred? Well, the fact that this double bond disappears shows you that the difference between that alkene and that alkane. All right, so now I'm saying these words, and we'll talk about what those molecules are in later chapters. But my point here is that you can immediately see the difference between this molecule and this molecule. I've lost this double bond between these 2 carbons. And even though it's not explicitly shown, you should realize, oh, this carbon now has an extra hydrogen, and this carbon has an extra hydrogen. Right? Because over here, this carbon had only 1 hydrogen, and now here it has 2. Okay? Because instead of having that 3rd bond, it has to get, an extra bond to a hydrogen. Likewise, this carbon here has 4 bonds, and so there are no hydrogens, but this carbon over here has 3 bonds, so there must be a hydrogen on that carbon now. Okay, so anyway, my point here is that we can quickly look at this and just intuitively figure that out. Okay, so talking about functional groups, you should get comfortable with recognizing those. There are different types of functional groups, and the way most of this course will be broken down is we'll look at different functional groups and the types of reactions that they do. Okay, but first, let's get a feel for those different functional groups. So, simplest functional group you might see is just having a halogen attached to your alkane. So you have what's called an alkyl halide or haloalkane, where your molecule has a halogen attached to it somewhere. Okay. Now we can also make a functional group by adding in unsaturated bonds. In other words, we can add in double or triple bonds between our carbons, and that gives us alkenes and alkynes respectively. Okay, so a hydrocarbon with only single bonds is called an alkane. Okay, and those are pretty unreactive. So one functional group we can add is put a double bond here. We call that an alkene. Okay, and over here we add a triple bond. We have a triple bond between two carbons. That's an alkyne. Okay. All right. So that then brings us to water analogs. So that includes things like alcohols and ethers. So here are examples of those. So basically, if you take water, right? If water is seen as, as H2O, looks like that. If we swap out one of those hydrogens for an alkyl group, it's represented with the letter R here, so it's some hydrocarbon, some carbon chain with hydrogens on it. Okay, we call that an alcohol. All right. Likewise, if we swap out both of our hydrogens for our groups, we have what's called an ether. Okay. Now, thiols are also considered part of this family. A thiol is like an alcohol, except you've got a sulfur instead of an oxygen. Okay. Then we have the carbonyls. So a carbonyl is where you have a carbon double bonded to oxygen. Okay, so if you see that functional group, okay, that carbon-oxygen functional group, those are all carbonyls. Okay, so with that, I'll make a note of that here. Whoops. Let me erase that. Okay, so let's try that out. So if we have a carbon double bonded to an oxygen, okay. Generally speaking, this functional group that you see here is called a carbonyl. That's how that's spelled. Okay, so this includes ketones, where the two things coming off of your carbon are R groups. If you have an R group and a hydrogen, that's called an aldehyde. If you have an R group and an OH coming off it, that's a carboxylic acid. It's called that because that hydrogen is particularly acidic. And again, we'll talk way more about each of these functional groups in turn. We'll get into more detail on those in a little bit. Okay, so so don't stress too much about functional groups yet. We're going to go into more detail on them. Just be ready to recognize them roughly, at least, or recognize that there is a functional group present. All right, so that brings us to drawing atoms with formal charges in our bond line structures. Now, you remember back when we talked, when we looked at our Lewis structures, we saw that sometimes you have to give atoms formal charges, because if you were to break those bonds homolytically, if you look at the number of electrons immediately around that atom, it might not correspond directly to the number of electrons that your element would have had if it were an atom by itself. So, in other words, the number of valence electrons that your periodic table tells you it ought to have. Okay, so for example, oxygen is in group 16 or 6A, and so it has 6 valence electrons. Now, if we look at this oxygen over here and we drew a circle around it to sort of say, okay, how many electrons are assigned to this oxygen the way it's drawn. Okay, so if we break any bonds, we're just counting 1 electron per bond. Okay, because you can assume that this bond, for example, is split in half. 1 electron goes to the hydrogen, 1 goes to the oxygen. Okay, so we count that as 1 electron for the oxygen. So that's 1, 2, 3, 4, 5 electrons. But oxygen ought to have 6, right? If it were a neutral oxygen atom. So since this is drawn as having influence over only 5 electrons, that we give it a positive formal charge, right? So that's something to keep in mind. Okay. So basically, whenever you look at a molecule like this, you want to be ready to assign those. The reason for this is that sometimes drawing our bond line diagrams, because we lose a little bit of information, it you want to have that formal charge labeled so that people are aware of that formal charge on your molecule. It might not be intuitive in the way it is in a Lewis structure. Okay, so take a second and have a look at all of these atoms and see if you can assign formal charges to any atoms that need it. So obviously if an atom is neutral, you don't need to write a formal charge to it. So for example, if I look at this oxygen up here, it's got 1, 2, 3, 4, and then one each of these electrons. So that's 6 electrons to that oxygen. This oxygen over here is neutral. Okay, so it doesn't need a formal charge. Okay, so go ahead and pause this video and assign formal charges to the molecule. Okay. Okay, so here are your formal charges, and you can see that the only things that with formal charges are that oxygen I pointed out earlier. This oxygen over here has a -1 formal charge, right? So it's got 1 electron from this bond with carbon, and then another 6 electrons from its lone pairs. So that's 7 electrons in total, so that extra negative charge is because it's in charge of an extra electron. This nitrogen here has 4 bonds and therefore it has 4 electrons in its vicinity, but nitrogen should have 5 valence electrons, and that's why this has a positive formal charge. Okay. You can assume from all of these that these carbons are all neutral, and again they're labeled as neutral because it's not shown, but they've got bonds to hydrogen which help them meet that octet rule. So each of those carbons has 4 bonds, which means they have 4 valence electrons if they were alone, and that's how many valence electrons they should have as a non-bonding carbon atom, and that's why it's neutral formally. Okay, so why is this important? Well, in the case of carbons that do have a formal charge, because we're not drawing those hydrogens, we have to have something in that diagram that shows you that it has that formal charge, so you know that when you are counting the number of hydrogens, it's not going to be the number you expect. So for example, let's say we look at a carbocation, right? A carbocation is a carbon atom that has a positive formal charge. Now the reason it has this formal positive charge is that it's missing a hydrogen. Okay, that carbon has only 3 bonds, and because it's missing a 4th bond, that's where that positive formal charge comes in. Okay, so if you see a carbon with a positive formal charge on it, just realize it has 1 fewer hydrogen than you would expect. So if you see a carbon with 3 carbon-carbon bonds, okay, normally you'd say, oh, there's a 4th bond to a hydrogen. But when you see this positive formal charge, realize it has no hydrogens attached to it. Okay. Likewise, over here, there are 2 carbon-carbon bonds, so normally you'd think there'd be 2 hydrogens, but because of that positive formal charge, you know that it's missing 1, so instead of 2 hydrogens, it only has 1 hydrogen. Likewise, you normally think of a terminal carbon as having 3 hydrogens on it, but if it's got a positive formal charge, it has only 2 hydrogens. Okay. Likewise, you can have carbanions. A carbanion has a negative formal charge. Now, the reason for this is that instead of just having, hydrogens and an empty orbital, it has an extra lone pair. Okay, so it has one of its hydrogens swapped out for a lone pair. So if you count the number of electrons around this carbon, that's 5 electrons, hence the negative formal charge. Okay, so 5 electrons instead of the 4 you would expect for a neutral carbon. Okay, so again, when you see that negative formal charge on a carbon, realize there must be a lone pair on that carbon. Okay. Likewise for heteroatoms, sometimes to make your diagram less cluttered, we leave out things like lone pairs and so on. So having formal charges on your heteroatoms also helps avoid this confusion. Now, sometimes you do get people who put lone pairs in their bond line diagrams just because it sometimes makes more sense to see what the lone pairs are doing, but it's good to get into the habit of writing out formal charges just in case lone pairs are omitted. Okay, so something to watch out for when you're working backwards here and you see just see a nitrogen without lone pairs, without formal charges written. You want to be ready to determine how many electrons must be on that nitrogen. Okay, So if it's drawn without a formal charge, you can assume it's neutral, and it's actually a nitrogen radical. Okay, over here with an unpaired electron to make it have 5 electrons. Okay, so that being said, if you see that formal charge, you can go ahead and do that calculation to figure out how many electrons should it have. Okay, so for example, have a look at this oxygen here. You can see that this oxygen has a single bond, okay, but it has a negative formal charge. So how many how many lone pairs are on this oxygen so that it has this negative formal charge? Well, remember, oxygen ought to have 6 electrons. It's in group 16, or group 6A. And so if it has a negative formal charge, that means it actually has 7 electrons, right? So if one of those electrons is tied into this bond here with carbon, there must be 6 electrons in lone pairs around this oxygen. Okay, so that means that there should be 3 lone pairs that you would draw on that molecule. So you see an example here. Here's what that oxygen looks like with its 3 lone pairs giving it that negative formal charge. Conversely, if you have a positive formal charge on an oxygen, you know that it's going to have 3 bonds and a lone pair. That gives it 5 electrons instead of 6 electrons around it, hence that positive formal charge. In order to get a neutral oxygen, that oxygen must have 2 bonds and 2 lone pairs. That's how it winds up with 6 electrons. Okay, so if you drew a circle around that oxygen, it gets 2 electrons, 1 from each bond, and then 4 electrons from 2 for each lone pair. Okay. Likewise with nitrogen, you can kind of do a similar system. So nitrogen is in group 5A, or group 15, and should have 5 valence electrons. Okay, so if it's neutral, it meets these 5 electrons by having 3 bonds and a lone pair. If it is, if it has a negative formal charge, right, it would have 2 bonds and 2 lone pairs. And if it has a positive formal charge, where it's an ammonium ion of some sort, it has 4 bonds and no lone pairs. Okay, so let's talk a little bit now about how to draw these molecules in 3D. The problem with drawing molecules or representing molecules is we're often doing this on paper or on a screen. Like if you're watching this on your computer, or if I was presenting this in class in a PowerPoint presentation, you'd be watching this on a flat screen. How do I represent a 3-dimensional molecule as a 2-dimensional drawing, right? So that's a problem we have to address. So there are multiple ways to do this, but the most common way to deal with this is to use solid and dashed wedges. All right, so a solid wedge tells you that that atom is sticking towards you. It's sticking out of the paper, out of the plane of the board, towards the viewer. If you see a dashed wedge, that tells you that that atom is sticking into the paper, into the plane of the board. All right, and of course anything that is not a wedge, if it's just a regular line, that means it's in the plane of the board or in the plane of the paper. Okay. So yeah, you can see how it's done. Oh, a quick note here with sometimes with ring compounds. So this carbon, so this is a bicyclic compound. There's 2 rings. There's a 6-membered ring on the outside here. Okay. And then there's sort of a 1 carbon bridge that's connecting these 2 carbons. So you could think of this as a 5-membered ring this way and a 5-membered ring this way. Anyway, my point here is that to show this in 3D, we have to show that this carbon is sort of sticking out. And since it's sticking towards you, that's why it has a sort of a thicker line representing that solid wedge. All right. There are different ways to show 3D structures, and we use them in different contexts. Depending on what you're doing, sometimes there's one way that's preferred over another. So for example, if you're a biochemist and you're drawing out carbohydrates, you'll see that the most popular ways to do that are to use a Fisher projection or a Haworth projection. Okay, so both of these are actually very common for biochemists to represent those molecules. So, and again, when we get to Chem 204 next semester, towards the end of Chem 204, we will do a chapter on carbohydrates, and I'll show you how to draw these structures, okay, and how they translate into molecules as we know them. But anyway, my point here is that these are examples of showing 3D. So each of these crossroads, these intersections in your Fisher projection, represents a chiral carbon, a carbon with 4 different groups attached to it. And so it's understood that the bonds coming off of, going from left to right on your intersection, those atoms are sticking towards you, whereas the carbon backbone going from north to south, from top to bottom, those are sort of pointing away from you. Okay, that's just how Fisher projections are drawn. Okay, likewise, in a Hayworth projection, you're usually showing a ring compound. So usually when carbohydrates are in solution, they form a ring. And the way you're drawing this is you're kind of putting the ring into, it's kind of lying sort of flat, sort of sideways, where these atoms down here are closer to you. Okay. Likewise, when we draw cyclic compounds, you'll see that there are certain ways to draw, your atoms. We just get used to drawing our rings in a particular fashion. We'll get to cyclic compounds a little bit later on. I think I talk about them in the chapter on alkanes, and I'll go over how to draw these with you. Okay, and try and get them. Try and get you to get comfortable with drawing this so that you're able to recognize what this looks like in 3D, even though you're seeing it as a 2-dimensional drawing. Okay. Now, you probably covered resonance back in Gen Chem when you were learning Lewis structures. So just to jog your memories, resonance is where the electrons in your Lewis structure aren't really tied down to one location as shown by the Lewis structure. They're actually kind of spread out throughout the molecule. And when you're drawing Lewis structures, you can draw one Lewis structure versus another, but in real life, the molecule is probably an average of all of those resonance structures. Okay, so for example, here we have an allyl carbocation. So that's where you have a double bond to a carbon-carbon double bond that is 1 carbon away from a carbocation. Okay, now there is another way to draw this. Basically, if these electrons in this pi bond swing over here, and they wind up bonding, filling in between these 2 carbons, this carbon now, which has only 2 hydrogens attached to it, winds up getting that positive formal charge. Okay, so in real life, though, the molecule, your allyl carbocation, is an average of those 2 things. It's both of these carbons have a partial positive formal charge. Both of these carbon-carbon bonds have some double bond character to them. Okay, so if you want to see why that is, you've got to think back to hybridization and look at what those atoms are doing. Okay, so it turns out that all 3 of the carbon atoms that you're looking at are sp2 hybridized. Okay, so in this case, this positive charge is housed in an empty p orbital, and in the other one, you've got 2 sets of unhybridized p orbitals making that pi bond. Okay, but you could easily swing that pair of electrons over and form the pi bond between these 2 p orbitals, and now this orbital over here is empty, and that's what puts the positive charge on that carbon. Okay, so in real life, those electrons are spread out between all 3 of these orbitals, and that's why both of these have some partial pi character. Likewise, both of these carbons have a partial positive charge. Okay, so if you want to see what that looks like from a molecular orbital standpoint, this is kind of what the orbitals making that up looks like. So you have the bonding molecular orbital where all 3 of those p orbitals are in the same phase. Okay, you have the non-bonding one where that middle one's just out of phase, and then you have the anti-bonding one where all 3 of them are out of phase with each other. Okay. So again, that helps, shows the three possibilities. Now, where are those electrons actually going? Well, there's two pi electrons, and those wind up in that bonding molecular orbital. That's why your allelic carbocations tend to be very stable in general. So, quick note here about molecular orbital terminology. You may hear the terms HOMO and LUMO used to describe particular molecular orbitals. So just in case you come across those terms, I should break down those acronyms for you. HOMO stands for highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. So where are the electrons in this diagram again? Now remember, we have only 2 pi electrons here. So if we represent the orbitals, let's say I've got lines representing these empty orbitals. Okay, so I'm going to draw if I've got 2 electrons here, they would go into this orbital for our bonding molecular orbital. Again, this is why this molecule is so stable, right? It only has electrons in that bonding molecular orbital. The reason there's only 2 electrons up here, if you counted all the electrons in this molecule, if this were neutral, there would be another electron, and it would go into this non-bonding orbital over here. Since we have a positive charge, we're missing that electron. So while this would have been the highest occupied orbital, the highest orbital with an electron in it, because this is now empty, this becomes the lowest unoccupied molecular orbital. Okay, so again, if you're not familiar with these terms, this becomes since this orbital is the highest energy orbital with electrons in it, this is the HOMO, the highest occupied molecular orbital, and this one, the next one that's empty, so this is the first orbital that's empty, that's unoccupied, that's the LUMO. Okay, and the HOMO and the LUMO combined are known as the frontier orbitals. So usually when you're using molecular orbital diagrams to describe chemistry, it's usually these frontier orbitals that are important, because anything that's interesting that's happening involves electrons either leaving the HOMO or going into the LUMO. Okay, whether you're promoting an electron up or something donates electrons into that LUMO, etc. There's something going on with these frontier orbitals, and that's where most of the chemistry is happening, where the reaction's actually taking place. Sorry about that little tangent, but I just figured this is as good a time as any to talk about those terms since they came up. Okay, anyway, moving on. Basically, if we look at our HOMO here, our highest occupied molecular orbital, notice that complete overlap, okay, of all 3 of those p orbitals. And this kind of really highlights where that positive charge is in our resonance structure. It's really spread between all 3 of those. Now, if we were to draw a resonance structure for this molecule, okay, this is how it was drawn originally, but you could recognize that I could have easily drawn my double bond on this side and have my positive charge on this side instead, on the left. And that's why there are 2 ways to draw this molecule, and we show this by using this double-headed arrow to show that these 2 are resonance structures of each other. You'll sometimes see this drawn in square brackets as well, that both of these are resonance contributors. Now, what do I mean by resonance contributor? While a Lewis structure is a convenient way to draw a molecule, when you have more than one Lewis structure, you have to realize that your molecule is actually an average of all of these. So even though you would draw a Lewis structure for either one of these, because you can draw them in more than one way, the molecule actually exists in both ways at once. Okay, so that's why they're called contributors. They sort of give some of the character of the molecule. Okay, if you combine them together, you get a better picture of what the molecule actually looks like in real life. Okay, so you might sometimes see this resonance structure drawn as what's called a hybrid. So if you were to take an average of these 2 molecules, so this resonance structure has a positive charge on the right carbon, this one has it on the left carbon. So if we were to average that, we would have partial positive charges on both carbons. Likewise, I have my double bond on the left, and over here I've got my double bond on the right. In reality, that double bond is kind of spread between both halves of the molecule. So I use a dotted line here to show that partial double bond character. Okay, so sometimes you'll see these molecules drawn out as a hybrid. So that reflects what if the molecule looks like in real life a little bit more. But of course, this is sometimes inconvenient when we're trying to describe chemistry around a molecule. So we'll instead choose to draw one of these resonance contributors instead, one of these Lewis structures. Okay, so something to keep in mind about the nature of molecules that exhibit resonance. Now, quick note here about the arrow, this double-headed arrow. This is not a reaction arrow. This is not a molecule that is sometimes flipping, like, it starts off in one molecule and then changes into this other molecule and just flips back and forth. Okay, that's a kind of an incorrect way of looking at resonance. Okay, you may have heard it described as that way because sometimes that makes resonance a little easier to understand. In real life, it's actually more like it really looks like this hybrid structure where it's really kind of both structures at the same time. Okay, I think the analogy your book uses is to think of it like a nectarine, right? So a nectarine is a fruit that is part peach and plum. It's made by combining those two fruits to make a new type of fruit, right? Now, it's not like when you're holding a nectarine that if you look at it 1 second it's a peach and you look at it another second it's a plum. No, it's always a nectarine, right? It's both a peach and a plum at the same time. So that's how I would recommend thinking about resonance structures. Okay, so we say that the electrons in that pi bond are delocalized. They're spread out between both of these bonds, and that's why we use that dotted line to show that those 2 pi electrons are actually spread out here. That's what it means to be delocalized. They're not stuck in one location, they're spread out. Okay. Likewise, we also have a delocalization of charge. That positive charge is spread out between both of those terminal carbons. In both cases, this is what makes that molecule more stable. If you can delocalize charge rather than sticking it to one place, that generally helps sort of minimize the repulsion felt by those electrons and generally makes your molecule more stable. So that's a general rule of thumb you want to keep in mind when you're thinking about the stability of molecules in general. So typically a molecule that can undergo resonance would be more stable than one where those electrons are stuck somewhere where they might destabilize the molecule, such as in a non-bonding orbital or an anti-bonding orbital. All right, so that being said, while hybrid structures are great for showing what a molecule looks like more in real life, as I pointed out, it's sometimes more convenient for us to use regular resonance structures, resonance contributors. So you should be ready to draw to see how one resonance structure could be flipped into another. Now, to do this, we have to show these electrons moving between one resonance structure and another. Even though those electrons in real life are spread out between all possible locations, it's important for us to be able to draw them as if they were moving. Okay, and to do that, we have to use curved arrows or curly arrows. A curved arrow shows the movement of a pair of electrons. This is represented with the double head of the arrow, right? It's a double-headed arrow. It's got a regular arrowhead. Okay. In a later chapter on radicals, we're going to use fishhook arrows or single-headed arrows, and those will involve the movement of one electron at a time, or single electron transfer, so to speak. Don't stress about that for now. We're not going to deal with radicals until we get to, I believe it's chapter 11. So you've got some time to worry about that. For now, we're just going to deal with electrons moving in pairs, and that's the more common movement you guys are going to see in any way. Okay, now how do we draw these curved arrows? You want to have the tail of your arrow starting with where the electrons were in your previous resonance structure, and you want to draw the head of the arrow pointing out where they're going to be in the next resonance structure. Okay, so quick break down rules here. Actually, I guess I can, let me show you what this molecule would look like when that arrow is drawn. So if I have this resonance structure and I want to show like this is a resonance contributor, so these electrons are, so I'm moving these pi electrons, that's where the tail of my arrow is starting. So it's telling me that these two pi electrons are what are moving over, and they're going to move over to this bond here. So this bond goes from being a single bond to having a double bond because it's going to get those pi electrons. So our molecule is going to look like this. Okay. Now this carbon is no longer going to have a positive charge because now this carbon is going to have 4 bonds. Previously it only had 1 hydrogen, that's why it had a positive formal charge, but now that it's got that double bond, that carbon has 4 bonds and therefore is neutral. This carbon, on the other hand, instead of having 4 bonds, because it had a double bond here and 2 hydrogens, now it still has 2 hydrogens, but it only has this single carbon-carbon bond. So that's 3 bonds in total, which means that this carbon has a positive formal charge. Okay, I kind of drew that attached there. That should be floating around. Anyway, so that's what that molecule should look like. Okay, so with that in mind, though, let's talk a little bit about the rules we want to keep when we are showing resonance arrows. So basically, you don't want to break any single bonds. You've got to watch out for any steps that would have that. That's not resonance, okay? You're not going to break a sigma bond in resonance, okay? It's possible to break sigma bonds in a chemical reaction, and we will use curved arrows to show those, but it will not happen in a resonance. So again, notice that here we have a double-headed arrow to show that these are 2 resonance structures. This doesn't make sense if we're going to break this bond here. That wouldn't be resonance. Okay, when you are pushing your electrons to a new location, you have to make sure that location makes sense. Now, what this means is you do not want to wind up with an answer where your new resonance contributor has an atom breaking the octet rule. It is possible to break the octet rule for an element in period 3 and below, so there are exceptions here where you can do that. However, periods 2 and period 1 as well, I suppose, but period 1 is hydrogen and helium. They follow a duet rule. But period 2 includes elements that only follow the octet rule. You cannot exceed the octet rule for any period 2 elements, the second row elements. So you have it's just there's too high an energy gap to the d orbitals. Basically, there's not enough room to sort of play around with electrons like you can do with larger atoms. So my point here is that if you wind up with a resonance contributor that would create a resonance structure that has an atom exceeding the octet rule, that's wrong, because that resonance contributor would not exist. So here are examples of where that happens. So if these electrons were to swing to this oxygen-carbon bond, okay, this carbon would now have 10 electrons around it. It would have 2 electrons from each of the bonds with hydrogen, so that's 6 electrons there. But now this single bond would become a double bond, so that's another 4 electrons there. And that's 10 electrons, which is wrong. Same case for all of these bonds here. The oxygen or nitrogen, respectively, would have 10 electrons instead of 8. Okay? Have a look at this example. Is this an example? Is this allowed from a resonance standpoint? Okay, so if these electrons swing over here, they turn the single bond into a double bond. Is that okay? Okay, now, here's where you've got to get comfortable with looking at, with recognizing hydrogens being there, even when they're not explicitly drawn. Think about what this molecule looks like. Okay, if you were to draw this as a Lewis structure. So if this carbon has 2 bonds, right, it must also have 2 hydrogens, which are not shown. Now, can these electrons swing here? If these electrons moved here, so we had a double bond here, now I've got 5 bonds to this carbon. It's to use the nickname for it, that's a Texas carbon, and that's a bad thing. Okay, you do not want to have 5 bonds to your carbon. That is incorrect. All right, it is possible to go under the octet rule. Okay, that does happen. It might not necessarily be a good thing, especially if you wind up putting a positive formal charge on a very electronegative atom. Okay, but that being said, it is possible to do it. That's why, for example, we can have things like carbocations. Okay, so this carbon is under the octet rule. It only has 6 valence electrons drawn around it. Not ideal, but it's okay. Okay. Alrighty. So yeah, so here's an example of where that's happening with resonance. Okay, and so we can draw a resonance hybrid that looks like this, where you have a partial positive charge on that carbon, a partial negative charge on the oxygen, and that carbon-oxygen bond has some partial double bond character if you were to average these two resonance contributors. Okay, so with that being in mind, let's practice drawing this out. So if here we have one resonance contributor, and we are showing these electrons moving accordingly. Okay, so notice that these electrons have to move in conjunction, by the way. If these electrons swung here to form a double bond, but these didn't move away, this carbon would have 5 bonds around it, right? It would have a double bond here, a double bond here, and a single bond here. That's 5 bonds, or 10 valence electrons, and that carbon's a Texas carbon, okay, which again you don't want. So you have to have these move in a concerted manner. These electrons have to swing here as these swing here. So let's draw what that looks like. Okay, so if we draw, this would go where that arrow is. Actually, do I have it in the next slide? Oh, never mind. I've got it in the next slide. Let's not bother drawing it. But basically, you could see that, again, these electrons swing here to form this double bond that we see over here, and these electrons swing over here. Now, notice, by the way, that they're not going, that the arrowheads are not pointing to a bond, but it's pointing to that atom, that carbon atom. So that's why those electrons show up as that lone pair. Okay, that's on that carbon, turning into a carbanion. That's why we've got a negative formal charge. Please note also that the tail of this arrow that swings down here, the tail originates on that oxygen's lone pairs. Okay, it's not starting from a bond, and that's why you're missing a lone pair on this oxygen here. Okay, and notice that this oxygen now has 3 bonds and 1 lone pair. Okay, so if you were to draw a circle around it, that's 5 electrons, and that's why that has a positive formal charge. Okay. So, that being said, now that we've seen the general rules over what we can and cannot do when drawing arrows for resonance structures, I recommend trying to notice the patterns that you will observe in systems that have resonance. If you can get good at recognizing these patterns, it makes it a lot quicker and easier to see where resonance is going to take effect, and also keeping in mind then where your curly arrows should go, and also it'll give you kind of an insight into what's going to happen. You start recognizing, like, oh, I've got this piece of a puzzle here, and that makes solving the puzzle a little bit easier when it comes to understanding bigger mechanisms. Okay, so the 5 situations you're going to come across are with allelic lone pairs. Okay, so basically you have a lone pair that's in an allelic position, that's 1 bond away from a double bond. You have a positive charge that's in that allelic position. You can also have a lone pair that's adjacent to a positive charge. You could have a pi bond between 2 atoms that have differing electronegativities. And finally, you can get a conjugated system of pi bonds in a ring. Okay, this is often seen in aromatic systems. We'll spend an entire chapter talking about aromatic systems in Chem 204, but for now, at least get ready to recognize where resonance is going to take over with these. Okay, so let's first explain what I mean by allelic positions. All right, I kind of referred to it before as being 1 bond away from a double bond. This is contrasted with a vinylic position. So you've probably heard the term vinyl with, for example, polyvinyl chloride, or PVC. All that means is that is, you basically have a chlorine that's attached to a double bonded carbon. So anyway, so what do I mean by vinylic position versus an allelic position? So a vinylic position is the carbon that is involved in the double bond, whereas the allelic position is 1 carbon away from that. Okay, so here we have, chlorines that are attached to double bonds that are vinylic chlorines, and then we have a chlorine that's that's attached to an allylic carbon, a carbon that's one carbon away from a double bonded carbon, and so those chlorines are considered your allylic chlorides. Okay, so if you paused and looked at this answer, you can see where our chlorines are either allylic or vinylic. Okay, please note that this chlorine over here is neither. Okay, because if you're looking at this double bond here, that's the vinylic carbon. This is an allylic carbon. This is one carbon past that, so that chlorine is neither allylic nor vinylic. Okay, so with that in mind, if you can identify your lone pairs as being allylic versus not, remember your allylic position is an atom that is not your double bonded atom, but one away from that. If you have a lone pair on that atom, we call that an allylic lone pair, and it can be involved in resonance. Okay, and you want to get comfortable with seeing that pattern. Okay, so let's look at each of these examples where we have a lone pair that's in an allylic position. Okay, and then draw the resulting resonance structure. Okay, so take a second and draw that. Feel free to pause the video, and I will go to the next slide and show you how this works. Okay, so here you can see this. I've kind of put carbons in here. I guess I didn't need to put those. I think that was an artifact of the structured drawing program I was using at the time when I made the slide. But so you don't technically need that carbon there. So if you left that off, that's okay. But basically, if you're having trouble seeing this, let me draw your arrows to show you what's going on here. So basically, when you draw your curly arrows, they have to originate with your allylic lone pair. Okay, so they're going to start with your lone pair, and they're going to swing to the bond where you're going to form that double bond. Likewise, now at the same time, you have to have this double bond, these pi electrons in that double bond, swing over to that further carbon where that's going to pick up that extra lone pair and turn into your anion. Okay, if you didn't draw this second arrow, this middle carbon would have two double bonds on it, plus the hydrogen that's not shown. Again, that's a Texas carbon and that's not allowed. So you have to have both of these arrows for this to work. Okay, let's have a look at this one. So again, here we have lone pairs on this oxygen. We're going to swing them to this carbon-oxygen double bond. But again, then this would turn this into a Texas carbon. So in a concerted step, so at the same time, these electrons swing to this carbon, giving it that lone pair and that negative formal charge. Again, you don't have to draw in this carbon, the atom itself, and if you want to put these formal charges in little circles, you can. So you could go and draw that. If you want to draw those with little circles, you're allowed to. Okay, and likewise, you don't need the carbon explicitly written out. Okay. Let's have a look at this one. So here we have our lone pair going from our oxygen to our bond, and from our pi bond to our oxygen, to our atom that's in that allylic position, or vinylic position. So again, notice that you wind up forming this pi bond here, and notice that this oxygen loses that lone pair, and that's why it has this positive formal charge now. Likewise, this oxygen gains a lone pair, so it's not shown, but this oxygen originally had two lone pairs. So it's gaining a third lone pair, and that gives it that negative formal charge. Okay, so if we look at this system here, okay, so here's our double bond, here's our allylic lone pair. Just to make things a little bit easier to see, I'm going to put in the lone pair on this nitrogen so you can see it. Okay, so this nitrogen has 2, 4, 6, 8 electrons around it. Okay, these electrons swing here, and these electrons swing up here to that nitrogen, giving it an extra lone pair and forming this pi bond. Now notice that this carbon, going from a carbon anion with a negative charge to a neutral carbon, because it has a double bond here, a single bond here, And it's not shown, but there is a fourth bond to a hydrogen in both these cases. Okay, so that carbon now has 4 bonds and is neutral. This nitrogen, on the other hand, has 2 bonds and 2 lone pairs. So if I were to draw a circle around that, that's 6 electrons instead of the 5 that nitrogen normally would have if it were an atom by itself. So that's why it has a negative formal charge. Okay, so here again, I'm going to put lone pairs just for clarity, or just to be able to see what's going on. These electrons swing down here to this nitrogen carbon single bond, turning it into a double bond. And then these electrons, of course, have to swing up to the oxygen. Otherwise, again, you would wind up with a Texas carbon. So you have to have these electrons swing up. And you can see that's why this molecule winds up getting, or this oxygen winds up getting 3 lone pairs and a negative formal charge. This nitrogen turns into an ammonium with its positive formal charge and 4 bonds. Okay, so I'm hoping that by doing this, you guys kind of get that pattern. Notice that in all of these cases, as soon as you see that allelic lone pair, you know that you're going to draw 2 curly arrows, one arrow from the lone pair to the bond next to it, and then the other one from the pi bond to the atom next to it. Okay, and that's, 2 atoms away from the atom that originally had your lone pair. Okay, so again, seeing that pattern when we draw it over and over again makes it that much quicker and easier to recognize. So this is why you kind of want to practice this skill, just to get comfortable at recognizing that pattern. Okay, just like with allelic lone pairs, we can do this with positive charges in an allelic position. Now, here, there's going to be only one curved arrow. Okay, so what's going to happen, okay, is your pi electrons are going to move from there to here. Okay, so it's still going to move to a bond. You're still going to form a double bond. Now, what's going to happen then is this carbon is going to have 4 bonds and lose that positive formal charge. But this carbon, because it's losing a bond, winds up getting that positive formal charge instead. Okay, so the resonance contributor for this is going to look like this. Okay, so you'd have a double-headed arrow between these two things. But that's basically what that contributor looks like. Okay, so unlike with an allelic negative charge, or with a lone pair where you've got 2 arrows, here you only need 1 arrow for this to work. Okay, now you can have a conjugated system where there are multiple double bonds that sort of alternate with single bonds. You have to be ready to draw multiple arrows if that's the case. So for example, I could have one of these shift over to make this intermediate resonance structure. Likewise, I could then have this shift over to this bond to make this intermediate. Or I could have drawn both of these in a concerted process to go directly to this. But my point is that you're going to need, be ready to see this system in chunks, right? So notice that here we have a resonance structure with an allelic positive charge. Likewise here, we still have that allelic positive charge. Okay. All right, another situation is where we have a lone pair adjacent to a positive charge. Again, these electrons will swing down here and form a pi bond, and that takes care of both, that takes care of that positive charge immediately. In this case, we had a negative charge, so that also becomes neutral. Now, if this were a neutral atom, it would wind up becoming positively charged. Okay, so that's something to watch out for. Like here's an example of that. Here we have a lone pair from a neutral atom going to form this pi bond, and that gets rid of this positive formal charge. And notice that now this oxygen with its 3 bonds and lone pair has that positive formal charge. By the way, this is a quick way to check your work when you're drawing resonance structures. Your overall number of charges should be the same in both resonance structures. So for example, here I start off with 1 negative charge and 1 positive charge, so that's neutral, right? My other resonance structure is also neutral. Likewise here, I've got only 1 positive formal charge in this whole molecule, and over here I also have only 1 positive formal charge in the whole molecule. Okay, so that's a quick way to make sure that you haven't made a mistake. If you wind up changing the number of charges, and they don't cancel each other out, you don't have the same net number of charges, then something's gone wrong. Okay, another situation, of course, is where you have a oh, sorry, this is the same situation. This is just with a nitric group. So go ahead and try drawing the different contributors here for your molecule. Now, this is an interesting case because unlike the other examples where we would draw just one arrow to get the positive charge to cancel out, you'll notice that you won't be able to do that with this molecule. So ask yourself why. If you're having trouble seeing it, try drawing that one arrow. So if you're looking at this molecule, ask yourself, what goes wrong if I take this lone pair and move it to form this double bond between this nitrogen and oxygen? Okay. Hopefully you've by now realized that if I form a double bond here and don't do anything else, that nitrogen has 1, 2, 3, 4, 5 bonds around it. It would be a Texas nitrogen, so to speak, but it would exceed the octeteral, and that's why you can't draw only the one arrow and be done. You have to have multiple arrows going ahead. So if you have one arrow going here, you must have another arrow going here. Or if you don't want to do that, you'd have that arrow swinging down here. Okay, so that leads to the multiple, resonance contributors. Now, for the arrow that's located down here, if we were to draw the swinging down here, it kind of depends what that nitrogen's connected to, because sometimes you might have something here that also would be influenced by the octeteral. If it's another carbon that already has 3 bonds, and this is their 4th bond, again, you can't only then draw the forming a double bond here, because then that carbon would have 5 bonds and you still have the same problem. Anyway, my point is that you want to keep, like, it's not shown here, this is just the nitro group, but you want to keep in mind if this were a real example, you would want to think about what's this attached to. Okay, so you can see here in the answer with our resonance contributors, you can either first draw these electrons moving here to kind of open up this resonance contributor where you have a 2+ formal charge on the nitrogen, and then these electrons swing down, or you could do it in a concerted process like I showed earlier. All right, so another situation is where we have a pi bond between 2 atoms of different electronegativity. Now, this is seen very often in the case of carbonyls, where you have a carbon and oxygen double bonded to each other. So you can see here these electrons swing up to the oxygen, which, being more electronegative, is okay with housing that negative charge. Likewise, you form a carbocation here, and this is one example again of a molecule sort of doing this form of resonance. By the way, please notice that this is the reverse of an example that we saw earlier. So if I go back a couple of slides, notice that here we're starting off with the carbon oxygen, with the formal charges on your carbon and oxygen, and they go back to the neutral form. Okay, so this is just that they're both resonance contributors to each other, is what I'm getting at. Likewise, here we have an imine, and this can also do that same system. So ask yourself, what would this look like? Where could we move these pi electrons? How would we draw this arrow? Okay, now when you're asking yourself that question, what you really should be looking at is, look at that carbon and that nitrogen, right? They are, that carbon and the nitrogen are both on that double bond. So ask yourself, which of these two is more electronegative? Okay, so look at your periodic table and look at where nitrogen and carbon are in relation to each other. Okay, the one that's more electronegative is probably going to take those electrons. Okay, and I guess I haven't got that drawn in an answer slide. Let's do that right now. So nitrogen is to the right of carbon, and so it's more electronegative. So those electrons are going to swing up to the nitrogen. And you wind up getting an extra lone pair in that nitrogen. This carbon's missing that bond now, so it has a positive formal charge. It's a carbocation. This nitrogen has 1, 2, 3, 4, 5, 6 electrons around it if we were to encircle it, okay, and split those bonds. So it would have 6 electrons instead of the 5 that you would expect for a nitrogen. So it has a negative formal charge. Okay. All right, so in an aromatic system where you have alternating single and double bonds, or what we call a conjugated pi system, you can have these electrons swing around like this in this concerted pattern. I think the most common place you see this is in a molecule like benzene, right? So in benzene, you might see benzene drawn either like this or like this. These are the two main resonance contributors, right? Now, because of this resonance, you'll sometimes also see benzene drawn like this. So you'll have the hexagon of those 6 carbon atoms, okay? But instead of drawing alternating double and single bonds, whether you draw them here, here, and here, or rotated here, here, and here, you just see the hybrid drawn with a circle to represent the delocalization of all 6 of those pi electrons. Okay, so sometimes you'll see benzene drawn like this. Just understand that this is kind of a hybrid. What's really going on are these are the two resonance contributors. Okay, and again, you might just see benzene drawn like by one of these resonance contributors, and that's fine too. Okay. By the way, if you're showing the electrons rotating around here, you can draw those electrons going. In this case, they're drawn going counterclockwise. You can draw them going clockwise as well. That's fine too. Whatever direction, it doesn't really matter because, again, remember, it's really in all those places at once. It's not like the electrons are moving clockwise or counterclockwise. The curved arrows are just for us to help understand why these are two resonance structures of each other. Okay, so just to summarize, these are the 5 ways, the 5 patterns you typically see resonance. So be ready to recognize these because that'll come in handy not just only for drawing resonance structures themselves, but also when molecules with these resonance patterns are involved in reactions. Knowing their resonance structures will give you an insight into why they undergo certain mechanisms. Why do they, do the reactions that they do? Okay. So with that in mind, here's another practice problem. So look at this molecule and go ahead and draw out all the resonance contributors for this molecule. So try and identify all of these different patterns in that molecule. Okay, so for example, notice that we have where you have a double bond, think about what's in that allelic position next to those double bonds. Okay, anywhere where you have a positive or negative formal charge or lone pairs in an allelic position, think about how they might be moved around. Okay, so go ahead and pause the video and go from there. Quick note here. Please note that you've got a few sp3 hybridized carbons, those that have 4 bonds, and because they have four bonds, they're not really going to take part in resonance. You're not going to break a carbon-hydrogen bond here to do resonance. There are situations where we can break a carbon-hydrogen bond to do reactions, but not technically for a resonance structure. So here's the answers. These are, again, the various ways you can push around your electrons, and these are all the different resonance contributors. So if we look at this, this is the original molecule that's drawn over here, okay, and you can see that we can push electrons around to get the various other resonance contributors. So look at how each of these are different. So for example, if we move these electrons here, okay, that's what causes this double bond to form. Now this carbon no longer is a carbocation, but this nitrogen is an ammonium ion. That's why it picks up the positive charge. Okay. Likewise, if we were to take this molecule, actually it looks like we've got the original molecule here drawn. We've got that same pattern here. But if those, notice that here we're forming. Notice that here we're forming a carbon-oxygen double bond, right? So those electrons had to have come probably from here. These electrons would swing over here. Now this can't be the only arrow because otherwise these electrons, this carbon over here would be a Texas carbon. So these electrons also have to swing somewhere. And it turns out that since we've got this negative formal charge here, and that carb anion, these electrons probably swung to that carbon specifically to give it that lone pair. So that's kind of what happened in this region over here to get this resonance structure. Okay, and likewise you can keep going through and seeing how we got each of these. So for example, instead of swinging to this carbon, if these electrons swung up to this bond here. So for example, so if I had these electrons swing over here, and these electrons swing over here to that carbon-carbon bond, okay, that's where we get this resonance contributor over here. Okay, and so on. So let's see what else we could do. We could have these electrons swing, from this resonance contributor. Okay, if we kind of combine this resonance contributor and this one to make this contributor here. Okay, so notice that we've got this system here where these electrons have formed this pi bond and this ammonium ion. We've combined this system here where we got this carbon oxygen double bond and this carb anion. So if we combine both of these two contributors, we get this contributor here. Okay, or alternatively, now notice that we have a pi bond here with a carbon and nitrogen, which have different electronegativities, so we can easily move these electrons to this nitrogen, and that's what creates this system here. Okay, so anyway, my point is that there are different ways this molecule has multiple sites for resonance. This is why it's a good practice problem for trying to see, where these electrons are going. Okay, and I'm sure there are other ways to combine this as well. All right, now, if we're going to continue our discussion on resonance, up till now we've kind of treated all of our resonance structures as equivalent, right? We've kind of got this even split between our resonance contributors. So if we look at using a nectarine analogy and looking at the molecules we kind of used previously with those, we kind of treated it as being a nectarine as being an even split between a peach and a plum, like as being equally a peach and a plum, right? The resonance contributors making that hybrid are even. You've got a resonance hybrid that's exactly like both of those combined. However, there are situations where one resonance contributor might be more stable than another, okay, or another one might be less stable. And as a result, they don't contribute equally to your hybrid structure. So when you're looking at that molecule and you're trying to think about, okay, what does this look like in real life? What does this hybrid look like? You've got to kind of take that stability into account. So the analogy here is if you had a fruit that was made up of different percentages of different other fruits. So if a nectarine is 50% peach and 50% plum, what would you have if you had a fruit that was 65% peach, 34% plum, and 1% kiwi, right? Like that would look different than a nectarine. So in the same way, when we look at our resonance contributors, we need to evaluate how stable are these individual contributors, and how does that affect the stability of the molecule? What does the resonance hybrid of that molecule look like? Okay, so generally speaking, it's going to, if I go back to that analogy, this fruit that's kind of weird, since it's got mostly peach characteristic, it's going to look more like a peach than the other things. In the same way, our resonance hybrid will probably resemble its more stable contributors. Okay, so what makes a resonance contributor more or less stable? And again, this, by the way, is why we do get into that habit of drawing resonance contributors. It helps us understand what the hybrid must look like. So basically, you want to look at where your formal charges are and how many you have of them. Okay, so typically speaking, formal charges do decrease stability. This is why one of the rules for drawing Lewis structures is you want to draw them with minimal formal charges, right? And so generally speaking, if you have a resonance contributor with more formal charges or higher formal charges, those are going to be less stable. What it also makes these unstable is when you have formal charges on the wrong type of atom. So for example, if you put a positive charge on a relatively electronegative atom, like an oxygen, for example, that's pretty unstable. Okay, and vice versa. If you have a negatively charged atom that is normally has a pretty low electronegativity, that also doesn't make as much sense. Okay, so generally speaking, a complete octet will also increase stability. So while we've seen examples of atoms that go under the octet rule, generally speaking, an atom is more stable if it's neutral and it has a complete octet. Okay, so here, let's try an example here. So here we have acetic acid. Now remember that oxygen, each of those oxygens has two lone pairs that aren't shown. Okay, so go ahead and draw resonance contributors for this acetic acid. Okay, if you need to pause the video, go ahead. But here are our three resonance contributors. Okay, so if we have our electron, we could split up that pi bond and get electrons up on that top oxygen, or an extra lone pair on that top oxygen, and of course turn that bottom one into a carbocation. And likewise, we could also swing a lone pair from this oxygen to form this pi bond over here. If you're having trouble seeing this, let me draw the curly arrows for you. So this oxygen actually has lone pairs. This one has two lone pairs as well. So what we're doing to get to here is these electrons are swinging up to that oxygen. Okay, so you wind up with three lone pairs on that oxygen. And this oxygen here still has two lone pairs. Okay. Now in this contributor, one of these lone pairs goes to this oxygen-carbon bond, and so again now you have three lone pairs still on this oxygen up here, and you have only one lone pair on this oxygen down here, and that's why it has a positive formal charge. Okay, so let's think back to what makes a good resonance structure. Remember, if atoms have their octet rule, that's good. And if you minimize formal charges, that's good. So let's look at what we have here. The first one is probably the most stable. Notice that everything is neutral, there are no formal charges, and everything's meeting the octet rule. So far so good. Now, look at this Lewis structure. We have a negative formal charge and a positive formal charge. And we also have an atom that is under the octet rule. Okay, so again, that's why this is not as stable a resonance structure. This one's okay, I guess, but this one's definitely the most stable out of all three of these resonance structures. For similar reasons here, notice that we have formal charges here. Everything at least is meeting the octet rule, but we do have formal charges, and that's also why this is kind of not great. So if we were to look at the resonance hybrid of these, okay, they would have some partial negative charge and some partial positive charge on our atoms. Okay, but you have to realize that it's mostly looking like this. That negative formal charge on that oxygen is not as negative as you'd think it would be, despite the fact that 2 out of the 3 resonance contributors have a negative formal charge on there. Okay, let's try a similar exercise. So again, for this molecule here, this acetate anion, go ahead and draw the resonance contributors for that. Or feel free to pause the video if you want. Okay, so here are your resonance contributors, and let's ask ourselves which of these are stable and which of these are not. So here we have, notice that this molecule is, has a negative formal charge. It's true, but everything at least is meeting the octet rule, and at least that negative formal charge is on an oxygen, which is pretty electronegative. So again, not as stable as something that's completely neutral, but pretty good. All right, so it's an okay resonance contributor. Same thing with this one. This is kind of very similar, right? Now, what about this intermediate one here? Now look at the number of formal charges. We have 3 atoms with formal charges, so that's not good. Plus, we also have that positive formal charge, or that we have a lack of an octet here on this carbon, okay, on this carbocation. So again, with all of that going on, this is not a great resonance contributor, okay? So this doesn't contribute that much to the overall hybrid. So notice that we don't show a partial positive charge on that central carbon. Okay, here's another example. Go ahead and try this one. So here are your different resonance structures. So ask yourself which of these are going to be stable and which ones are not. Okay. So for example, this molecule here, which has four formal charges spread over 3 atoms, that's not going to be great, right? Plus that nitrogen's under the octet rule. So this is probably not a very stable contributor. Okay, this is not great. Likewise, this one also has atoms, you've got 4 atoms with formal charges, including one that doesn't meet the octet rule. So these 2 resonance contributors are not significant. Okay, whereas these 2 are a little bit better. Again, you have formal charges and things, but at least everything's meeting the octet rule. So these tend to have a little bit more influence on your hybrid. Now they've drawn the hybrid here with that positive charge. Notice that the nitrogen has a formal positive charge, not a partial 2+ charge or anything like that. But since the 2 more major contributors both involve that nitrogen being positively charged, notice that that's a formal positive charge. Okay, and again, these oxygens have partial negative charges. They've put a partial positive on this on the carbon, and they've kind of drawn only partial pi bond character. But I would say that this is going to be really closer to neutral, and this is going to be closer to a real double bond than you would think. And likewise, this is going to be closer to a single bond. Okay, and again, drawing these individual resonance contributors and recognizing that these 2 are less significant, whereas these ones are kind of okay. That kind of gives you more of an idea of what this hybrid really looks like. Okay, so yeah, so go ahead and practice this with this one here. Like, you can look at these molecules and determine if they have determine what the resonance hybrid is, and and assess the stability of these as well. Again, feel free to pause this video. So to show you the resonance contributors, so if I have this lone pair swing down over here, and it's going to get you'd form a pi bond here, and it would get rid of that positive formal charge. So the resonance contributor looks like this. Okay, so this oxygen is missing a lone pair because that lone pair went to form this pi bond in our new double bond. But that means that this oxygen then has 5 electrons around it if we drew a circle. And so that means it has a positive formal charge, which again you can readily recognize from the fact it has 3 bonds and a lone pair, instead of its 2 bonds and 2 lone pairs, which you'd expect in a neutral oxygen. Okay, so again, which of these is more stable, right? Both of these wind up with positive formal charges. The trade-off, though, is here we have a carbon that's going under the octet rule, so that's decreasing stability. Here, though, we have a positive formal charge on an oxygen, which is typically is pretty electronegative. So that's kind of the trade-off in stability for these two molecules. Okay. So in terms of what is worse, going under the octet rule is considered worse. So this is so this is a less significant resonance contributor compared to this one. Okay, so the one on the right is a little bit more significant than the one on the left. Even though both of them, of course, aren't ideal. Like, this one's probably just okay, but this one's probably less okay. Over here, here we've got a positive formal charge, so we can swing these pi electrons over to that nitrogen. So its resonance contributor looks like this, which of course turns this into a carbocation. Again, we have a similar problem where we've gone from having a positive formal charge on a nitrogen, which is relatively electronegative, uh, to having a carbon go under the octet rule. But again, the key thing is that, remember, when it comes to picking between the two, going under the octet rule here is considered worse than having a positive formal charge on a nitrogen. So this structure on the left is the more significant resonance contributor. Okay. All right. So basically, you want to recognize when electrons are localized versus delocalized. Again, just to jog your memories, electrons that are in resonance that can move around are delocalized because they're not stuck in one location, hence the name. And those that are stuck are called localized electrons. They're not involved in resonance. Okay, they stay there. So typically things that, for example, are in just regular sigma bonds. Typically, the delocalized electrons you see are involved in pi bonds or lone pairs. Okay, so how do those delocalized electrons work, right? We pointed out that it helps to have unhybridized p orbitals. When you have an overlap of those unhybridized p orbitals, that's where those pi bonds come about. Okay, likewise, those p orbitals house the lone pairs that we see, or they might house an empty orbital or a carbocation where electrons might be donated into to get rid of that positive formal charge. Okay, so my point here is that in order for delocalization, you can't have an sp3 hybridized atom where everything's stuck in place. Your electrons must be on an sp or sp2 hybridized atom for this to work. Kind of confusing when you see an atom that you think is sp3 hybridized, like by looking at it, it seems like it's sp3 hybridized. My point here is that it actually has sp2 hybridization in order for resonance to work. So here we have a carbamate where this lone pair and that nitrogen swing over to form this double bond here. And just looking at this, you might say, oh, that nitrogen is sp3 hybridized, right? It's kind of in a trigonal pyramidal structure, but in order for this to work, it actually has to have some sp2 hybridization, where that lone pair is actually in an unhybridized p orbital. You have p orbitals that are located in this oxygen, this carbon, and in this nitrogen, and there's overlap between the three p orbitals for that to work. Okay. All right. So here's a picture of what that looks like. Okay, so normally you would think, okay, that nitrogen's got, it's got 3 bonds and a lone pair. Like normally you would think that's sp3 hybridized, but instead that p orbital winds up being unhybridized to allow resonance between those 3 atoms. Okay, so that nitrogen, so even though you think it would be trigonal pyramidal, that lone pair would push the bonds that the nitrogen is connected to and turn into a trigonal pyramid. Instead, if you were to measure those bond angles, you would notice it's more trigonal planar. Okay, and so this is something you can actually determine experimentally. If you have an allelic lone pair, it can be used in resonance, as we saw in the example earlier. So even if your atom is sp3 hybridized, it can kind of have some sp2 character that allows that lone pair to be used in resonance. However, there are exceptions to this. There are situations where things can happen where that lone pair is forbidden from participating. Okay, so you've got to watch out for those. And this is an example of one of those exceptions. So here we have a molecule called pyridine, right? And you'd see this lone pair and you think like, okay, it's adjacent to a pi bond, it's in that allelic position. Can it swing down and form a double bond here, right? So if we did a concerted process where these electrons swung over here, formed this pi bond, and this pi bond swung over here to this carbon and gave it a lone pair, turned into a carbanion, why isn't that allowed, right? All these atoms, this nitrogen is sp2 hybridized to begin with, right? Why can't these electrons be used? Well, the key thing there is what I actually just said, that nitrogen is sp2 hybridized to begin with. The p orbital that's lined up with the other orbitals is is already being used to make this pi bond over here. What's going to happen is that lone pair is not that's housed in another p orbital is not going to be available right in the right plane to overlap. This will be a little bit more abundant in the next slide. So you can see here that p orbital on that nitrogen with the lone pair is used to form that double bond with the carbon next to it. Okay, so that other lone pair is actually in one of the hybrid orbitals. It's in an sp2 hybrid orbital, not in an unhybridized p orbital, and therefore it can't be used it cannot be used in resonance. Okay, so the key thing I want you to get out of this is think about where your p orbitals are on your atoms and realize that in order for electrons to be delocalized, they have to be in those unhybridized p orbitals. Okay. And that's it for this chapter. So let's go through the additional practice problems. I'll, show the answer slides. So again, feel free to pause on, for each of these problems and take a stab at the answers yourself, and then look at the answer slide to see if you got it right. Okay, so for this one, be sure to identify all your carbons and hydrogens. Okay, and then again, remember your carbons aren't labeled and any hydrogens attached to them are not labeled. So any points on your line, wherever it bends or at the end of any line that doesn't have an atom explicitly written, like the oxygen here, that would be anywhere else as a carbon. Okay, and likewise, any of those carbons, any bonds that are drawn explicitly are to atoms that are not hydrogens, but carbon needs to form 4 bonds. So find the number of bonds, a number of hydrogens by just subtracting from 4. Okay, so you should wind up with 11 carbons and 18 hydrogens. So in case you didn't, this 6-membered ring here has 6 of those carbons. There's a 7th carbon here, an 8th carbon here, a 9th carbon here. There's 10 and 11. There's all 11 of your carbons. For your 18 hydrogens, there's 3 on this carbon, another 3 on this carbon. These carbons have 4 bonds, so they don't need, this carbon has 4 bonds. This carbon has 3 bonds, so there's another hydrogen here. There's a hydrogen on this carbon. There's a hydrogen on this carbon. This carbon has 2 hydrogens. This carbon has no hydrogens. It's got 4 bonds to other carbons. And each of these carbons has 3 hydrogens. So again, that's 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and that 18th hydrogen is the one that's explicitly shown on the oxygen. Okay, so for these molecules, you want to draw bond line diagrams. I would start with a kind of a carbon skeleton and go from there. Okay, whoops. So yeah, so just practice that, and then the answers are over here. Okay, here you want to draw out formal charges. So again, you only need to do this for things that have formal charges. If they're neutral, don't worry about it. But if you're trying to figure out the formal charge for something, I recommend drawing a circle around it and then counting the number of electrons in that circle. Okay, and if it has, depending on those number of electrons, you should probably put in a plus sign or a negative sign for a formal charge accordingly. And the answers are here. So again, if you're having trouble seeing that, if I draw a circle around that oxygen, it's got 2 electrons from that lone pair, and then 1 electron each from its bond to carbon and to each of these hydrogens. So that's 5 electrons. Okay, so typically when you see oxygen with 3 bonds and 2 lone pairs, it has 5 electrons instead of 6, and that's why it's got a positive formal charge. Likewise, same thing with this nitrogen here. It's got, or sorry, not the same thing, but here if you draw a circle around this nitrogen, you see it's got 2 electrons, 1 from each bond, and then another 4 electrons, 2 from each lone pair. Right, so it's 1, 2, 3, 4, 5, 6 instead of the usual 5, and so that's why it has a negative formal charge. Phosphorus here, if we draw a circle around it, only has bonds, no lone pairs. And it's bonded to this carbon, this nitrogen, and 2 hydrogens. So that's 4 electrons instead of the 5 valence electrons that phosphorus should have, being in group 5a or group 15. Okay. This carbon, a carbanion, has a negative formal charge. It's got 1 electron that's sharing in each of its bonds with the nearby carbons, and it has 2 more electrons from that lone pair. But what really throws you off, because you think to yourself, wait a minute, that's 6 electrons. Why isn't it neutral? Don't forget, there is it's not shown here, but there is a bond to a hydrogen. So this is the one that I think a lot of students miss. Remember, this carbon must have a hydrogen attached to it to give it that negative formal charge. Okay. So actually, it's a little harder to see in a structure like this, but generally speaking, if you see a carbanion, know that it must have a negative formal charge and a lone pair. Okay. I guess if you got a problem like this that had a carbocation and they didn't, there'd be a lack of a lone pair and they don't show you the number of hydrogens. Doing a carbocation with this type of problem would be impossible, but in this case the lone pair is there, so you should be able to recognize a carbanion at least. Okay, and of course this oxygen here is neutral. It's got 2 bonds and 2 lone pairs, so if you count electrons around it, it's 6 electrons, and that's why it's a neutral atom. Okay. Let's work on this one backwards. Here we've got a molecule that's got formal charges drawn. Be sure to fill in the necessary lone pairs that you need. So here we have a carbocation, so this one's kind of backwards. There's not going to be any lone pairs in this. It's not shown, but there's going to be 1 hydrogen on this carbon that's not drawn. Okay, but that's why it has a positive formal charge. It has one hydrogen and 1 empty p orbital with that positive charge. There's no lone pairs in that. Okay, for everything else, look at the number of bonds they've got and ask yourself, all right, to meet the formal charge that they have, how many lone pairs how many more electrons does this need? Let's give it that many lone pairs. Okay, for this nitrogen, please note that it's got 2 negative formal charges on it, so that's the equivalent of a -2 formal charge. Okay, so if you want to check your work, here are those lone pairs added in. Okay, so when you look at those atoms, you can see that they correspond to the number of electrons that would give them that formal charge. Okay. All right, and now with a similar molecule, or the same molecule, go ahead and draw all the resonance contributors. So keep an eye out for negative formal charges and and lone pairs. It might be actually better to use this molecule here with the lone pairs drawn in if you want to see this. So start off with this molecule and ask yourself, where can I have, what resonance contributors can I get from this? So think about, for example, where you see a lone pair that's in the allelic position, okay? Or, for example, a positive charge that's in an allelic position, okay? Or, for example, a carbon and electronegative atom, like an oxygen, that have a pi bond between them. Okay? Or here we have 2 atoms that have a positive and negative formal charge. Maybe we could form a pi bond between them by swinging these electrons down. My point is here, there are lots of options. Okay, so here are multiple hybrids. So I guess I can draw in the arrows to show you what's going on here. So for example, if we look at the difference between these 2 molecules here, you can see that these electrons have swung over here to form the pi bond that we see over here. Okay. We could have, for example, let's see, what's the difference here between these 2? Oh, here we go. So here, notice that we have an allelic positive charge. So these electrons have swung over here, and that's what creates, gets rid of the positive charge here and forms this double bond. This carbon, of course, now is, is missing that extra bond, and that's what turns into that carbocation. Over here we have this again. Now we have an allelic, a lone pair in that allelic position where these electrons can just swing over here, and these electrons can swing down here as part of that, and so that's why we have this resulting canceling out of that negative and positive charge. So notice that this is still maintaining the overall charge of this molecule. Okay. Here we can get rid of that -2 formal charge by having these electrons swing to this bond here. Of course, we can't stop there, right, because we'd have a Texas carbon. There's a hydrogen that's not shown over here. So these electrons should then swing to that oxygen, which in turn then gets rid of that positive formal charge. So that actually works out really well, having this allelic system over here. Okay, so having that allelic system and having those electrons swing over actually alleviates some of that extra formal charge that we see. Okay, so if you want to see the resonance hybrid, again, notice that we have, if you can put together all of these resonance contributors, you have partial double bond character here and here. You can see how that double bond is kind of delocalized amongst these atoms. And notice how these atoms also have certain positive charges. Okay. Now, please note that nitrogen it's listed as having a partial negative charge, but keep in mind that that partial negative charge is between a whole negative charge and having two negative charges. So that's, even though it's listed as a partial negative, it's really like sort of like a partial double negative in a way. Okay, and that's it for this chapter. If you have any questions and stuff, please let me know. As always, be sure to try out some of the homework problems I've selected, and that are on that list on Blackboard. And if you want to do any extra problems, textbook problems, or go over them with me, just let me know during our class time. All right, have a great day.